Hi, I'd like first of all to thank you for taking a few minutes to just watch this video on the Hudson equilibrator. And of course it has a much longer name with the United States Patent Office, patent number 859-1449B2. And I'm Dennis Hudson, the inventor. This novel device can be thought of as a pump or as a shock absorber system or as an energy storage system. It's simple in construction and easy to fabricate, particularly claims 13 forward. All claims before claim 13 are rather complex. And what I propose to do here is to show you and assemble the device right before your eyes in a schematic form. Now there's also a licensing video at the website shown below, whattolearn.com/aerospace.htm. And I think you'll be very pleased with the licensing terms you find there. And the licensing window is only open for a limited time. First, let me briefly show you the more complex embodiments, those 1 through 12 embodiments of the device. And then we'll come to the very simple version. Your license, of course, if you obtain a license, would cover you for all embodiments of the invention as applied to the field of use of aerospace generally. Please see the license at the website for details. Alright, here we have one of those boxy embodiments I mentioned. I won't bother describing it except to say, well, to point out some features of it. This area right here, that's a flexible plastic bag containing hydraulic fluid. This middle part is a partition that goes up and down, and it slides along in a groove right here. This square right here is some sort of elastically deformable material, as is this square down here. So that could be a spring or a gas cylinder. And here's another version of the same invention, and it varies slightly. I won't bother explaining it. It's all in the claims. And now we come to the simplest embodiment of the invention, from which I'm going to assemble, as I said, right before your eyes, the device itself. Okay, just to orient the viewer, right here along this wall is a groove in the wall, and it's a tongue and groove arrangement. These two blocks right here are actually a partition. They can have more parts to them. And there's a tongue on the end of one, and it fits in that groove of that wall. And you have the same arrangement at the other wall with the other part of the partition. And of course what we're doing here is we're looking down inside the upper device. We've removed the top cover, and this lower view is we're looking down inside. Over here at the left, this dark heavy line, that's a flexible plastic bag. And inside it is hydraulic fluid, and to the left of that is a valve. Back here is an elastic material, a spring or a gas cylinder. Now let's move on to our schematic assembly of this device. Alright, you'll recall our spring. We're going to put that in place first. That goes up here like so. And then we'll put in place our partitions. And there's one partition sitting in there, and here goes the other one. It's going to sit over here. Then we put up the flexible plastic bag. It has some hydraulic fluid in it. And finally, we install the valve down here. Now, a main object of the invention is to enable you to be able to store a fluid under pressure and to dispense that fluid at a constant rate of flow without the interposition of complex valves and regulators. And of course this would apply to shock absorption, suspension systems, fuel pumps, and other devices. So what happens is, as we load the spring, or gas cylinder as it may be, as we load the hydraulic fluid into the flexible plastic bag, it pushes up on the partition, and these walls of the partition start sliding. They are slidably interlocked, and they slide apart along the walls and that increases the surface area that we're using to apply force to the elastic material. So as you can see, by expanding the surface of the partition by pressing on it with the hydraulic fluid and moving it upward, nominally upward, we compress the spring because we have expanded this surface and we have a fluid acting on that surface. So the total amount of force acting on the elastic material gradually increases in step with the compression of the elastic material. In other words, the return trip here, once we open the valve, would mean that we would get a constant rate of flow out of the valve of the hydraulic fluid, or for that matter, whatever fluid we pumped into it. Now, I did mention that it could be a spring or a gas cylinder. So permit me to assemble that version of the invention for you. And here we are. Let's begin. We have here a cylinder of gas, and we're going to put that in place by attaching it to the wall, the nominal rear wall of the housing, and then we're going to put in place, let's put in place first the hydraulic fluid bag, and then we're going to put in place the partitions. And we'll put one over here this time, and we'll put this one in place like this. Okay. And this right here is an extension of the shaft that comes out of, I just didn't have room to put it in the drawing properly, so now let's put that extension in so that it contacts, the shaft contacts the partition, and then we need to put the valve back in place as we had it before, and we'll put that right there. So what we have here is a piston and a gas inside the cylinder, and the piston contacting the gas, and a shaft coming out of the cylinder attached to the wall, and the shaft attached, or actually contacting the partition. So we have the same phenomenon, and we get a linear compression of the gas. Now that could be inside the device or it can be externalized. The patent covers either one. Now let's talk about some uses that you might find for this device in your industry. Now if you're in the area of rocketry, this one will be especially interesting, but it can also be applied to jets or conventional aircraft, propeller driven. Here, instead of a traditional fuel pump, we're using the invention as a fuel pump. And you'll note there's an A portion, an A bag, and a B bag here. In place of the hydraulic fluid, let's assume that B is fuel and A is oxidizer. This here is a dual aperture valve, and it's obvious that you can control the relative mixtures of fuel and oxidizer simply by varying the relative sizes of the bags. Also, you could control it at the valves with different settings on the valve. This makes for a very reliable fuel delivery system, and it's virtually impervious to G-forces or drastic temperature changes. And electrical interference doesn't bother it in the slightest. Now the deployment of it in an aircraft could look something like this, and I've exaggerated the sizes of the devices here. There are two of them. And the general idea is that you would have at least two. One would be pumping fuel out to the engines, while the other is being loaded from fuel from the wing tanks. Now here's a crude illustration of a shock absorption or suspension system. As you can see, there's a cylinder here in the upper left part of this, and down here we've opened the box a bit, and that would be probably a cylinder, but it doesn't have to be. And we have a shaft. It's a piston, actually. I said this was a cylinder. It's actually a piston. And as the piston is driven into the box, fluid is driven out and into the equilibrator. The rate of return from the equilibrator back to, as transferred back to the piston, is constant. Of course, this also has applications for opening and closing hatches and doors, raising landing gear, lowering the landing gear. Now this is a view of an emergency starting system. It's automotive in design, but the same principles could be applied to aerospace, and your license would cover you to do that. And as you can see, this is a truncated version of the equilibrator down here. And while the engine is running, it's charging up the equilibrator, and when emergency hydraulic power is needed, it's directed to a generator that will generate an electrical output to start or restart an engine in flight, for example. This claim relates to tire inflation, and you can just generally look at that and see how that works. It can be for emergency inflation or reinflation, or just to maintain a certain level of pressure. And here's another view of the same thing, more or less. So, this covers my presentation, and I do look forward to hearing from you soon. Thank you again for watching the video.